Section 3.4 is looking at the relationship between parallel and perpendicular lines. So we want to find the relationship between parallel and perpendicular lines. The important thing is that we're going to use the relationship of two lines and see how it relates to a third line to make decisions about whether or not they're parallel or perpendicular. In the opening example, they gave an example of two students walking home and cutting across a park. Now notice that the angle measures here are showing that these two angles are congruent. Notice that those are alternate interior angles, showing us that this court road is parallel to Schoolhouse Road. We also have this mark and this mark, which are also alternate interior angles, but these are alternate interior angles between Oak Street and Schoolhouse Road. So what we should notice between this, if Oak Street is parallel to Schoolhouse Road and Schoolhouse Road is parallel to Court Street Road, then all three of these should be parallel to each other. And that's our first theorem. It's just if two lines are parallel to each other, then they should also be parallel to the third. We can prove this by using a transversal and just noting the relationship. If these two are parallel, then their corresponding angles are congruent, and if the other two are parallel, their corresponding angles are also congruent. And so we can connect all of those and show that the two A and C should also be parallel to each other. Theorem 3.8 is looking at what happens when we have perpendiculars. Now notice they start with, in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. Now here's the proof for that. Our first step will be given R is perpendicular to T, S perpendicular to T. And then our next step will notice if they're perpendicular, then that means we have right angles. And this is our definition of perpendicular. Next, we should notice that all right angles are 90 degrees, so all right angles are congruent. And therefore, angle 1 is congruent to angle 2. If we now look at the position where angle 1 and 2 are, notice they are corresponding angles, and if corresponding angles are congruent, then our lines are parallel. So we'll write that as, looking at our picture, R is parallel to S. Sides are going to be parallel to each other. So in this particular problem, they're saying that our pieces are cut at 45-degree angles. They're wondering if when they piece them together, if our opposite sides are going to be parallel to each other. Well, in this one, all we have to do is add the 45 and 45, which will give us 90. Add the 45 and the 45, which gives us 90. We see that those two are same side interior angles. And if same side interior angles are supplementary, then we know the lines are parallel. The perpendicular transversal theorem is saying that if we have a perpendicular line, so just N is perpendicular to L, and we know that L and M are parallel, then we should be able to determine that this will also be a right angle down here, that those line M would also be perpendicular to N. Now, one of the key things that they mention here is in a plane, and this is important because I could have a parallel line or perpendicular line to line CA here that's going in the wrong direction, and it might actually be skew to line BD. If it's skew, then this would not be true, so they have to qualify this theorem with it's happening in a plane. Usually, unless they tell us otherwise, we'll assume that we're talking about in a plane. If we're going to prove this relationship, then we're going to start by noting everything that we have here. Now remember, the transitive property only works for congruence. We're not allowed to do that with perpendicular, so we're going to have to connect this in another way. What we do know is that because C and D are both perpendicular to B, they have to be parallel to each other. So C is parallel to D because two lines perpendicular to the same line are parallel. Now note, they did tell us that this is happening in a plane, which is why we're allowed to do that. But we can also see in this picture that this is in a plane. We also know that D was perpendicular to A, and so putting that together with this one, if we know that a line perpendicular to one of two parallel lines is also perpendicular to the other. And so we know that C must be perpendicular to A. And this is what we were trying to prove. Notice that rather than writing this out, we could have also used the shortcut perpendicular transversal theorem.